This lesson is on the subject of photoelectron spectroscopy, PES. So photoelectron spectroscopy is a way to determine the ionization energy of an electron. The ionization energy is equal to the energy of the photon minus the energy required to make the electron travel a certain distance. And a photon is a standard packet of energy delivered by light, and we will study photons in a later lesson. Ionization energy is also called binding energy. So the following formula gives the binding or ionization energy, and it is E ionization, that's the ionization energy, equals the energy in the photon coming in to strike the electron minus the kinetic energy of the electron once it's removed from the atom and is flying through space. So here's electron number 1. So imagine that a 20 joule photon strikes this electron. The electron then flies out and is measured to have a kinetic energy of 15 joules. That makes it travel. So if 20 joule photon caused electron number 1 to travel a distance that required 15 joules of energy, just like that, then there was 20 minus 15 equal 5 joules of energy holding the electron to the atom. So again, think about that. 20 joules comes in and strikes that electron. 5 of those joules are required just to break the electron away from the atom. That's it, just to get it to be removed from the atom. And then the final 15 joules that are measured by some device are the energy in the electron. So if you know how much energy went in, 20 joules, and you know how much energy the electron had coming out, 15 joules, then the difference between those two numbers would be the binding energy. It's the amount of energy that was holding the electron to the atom. So 5 joules is the ionization or binding energy. So 20 joules of energy was absorbed by the valence electron, which then had enough energy to escape from the atom, first of all, and then second, to fly a distance that required 15 joules of energy. It's needed to escape the atom. This is the ionization energy. Okay, so here we have again our 20 joule photon caused electron number 2 to travel a distance that required 8 joules of energy. So there it goes. There it is, 8 joules of energy coming out, and there goes the electron. So there was 20 minus 8 equals 12 joules of energy holding the electron to the atom. We know that that second electron would take more energy to remove from the atom than the first electron did. In this case, it's 12 joules of energy. So 12 joules is the ionization binding energy. AP usually asks students to interpret a PES diagram. A PES chart or diagram is read as follows. The vertical axis shows the number of electrons or relative number of electrons, since there are many, many electrons. The horizontal axis, that is the one that goes side to side, shows the highest to lowest ionization energies from left to right. So you can see the highest 1000 is on the left and the lowest 0.1 is on the right. So this means that the highest ionization energy, which would be in the 1s subshell, we know that those electrons closest to the nucleus are going to have the highest ionization energy. So this means that the highest ionization energy, the 1s subshell, will be on the left, and the lowest ionization energy, which would be out in the valence orbital, will be on the right. So each of the peaks below represents a subshell starting at the 1s. The height of the peak represents the number of electrons in that subshell. The element represented in the diagram can be determined by the number of electrons in each subshell. So the peaks on the graph are read as follows. The first one is the highest ionization energy based on the horizontal axis. That holds 2 electrons. That's going to be the 1s subshell. The next subshell, you can see, also holds 2 electrons, and that is the 2s subshell. It's at a lower ionization energy. The next one, the highest peak, has 6 electrons in it, and that's the 2p subshell. And finally, the last one, the last subshell there, is the 3s. And that you can see it's holding, while it can hold 2 electrons, it's only holding 1. So you can identify the identity of this element. The 3s subshell with 1 electron would mean that the PES diagram above is for sodium, Na. Normally, a graph shows the numbers on the horizontal axis from lowest to highest. So normally when you draw a graph, you show near the origin, you show 0, and as you go to the right, the numbers get higher and higher. Since the lowest ionization energy is in the outer orbital, this means that the valence orbital will be on the left and the 1s subshell on the right. So notice that the lowest energy on the left, that has to be the outer orbital, the electrons with the lowest ionization energy. So this means the subshells would be ordered as shown here. The 1s would be furthest to the right. You can see those are the bigger numbers on the horizontal axis, the higher ionization energies. Next would be the 2s with 2 electrons, and then the 2p with 6 electrons. Next is the 3s with 2 electrons, and then next would be the 3p with 1 electron. So here 1 electron is in the 3p subshell, which would represent aluminum. Alright, and that takes care of our lesson on PES, and you will likely be asked this if you're taking the AP, you will likely be asked a question on this.